Okay, so can you see the PowerPoint slide thing? Do you see the presentation view or the right view, or none of them?
Yeah.
Okay, cool. So this was the. Do you want me to go ahead and start, or are we waiting for somebody else, or should we go ahead?
You can see on your laptop.
Yeah, we're ready.
Okay. So this is kind of like what I was talking about the other day. This is, I think, where we left it. Well, we talked about a little bit about factorial designs afterwards, but this was kind of like a point that was a little bit confusing about how to control for the covariates, and then we discussed when sometimes you want to control for a covariate or not when doing a between group comparison. That was a little complicated. So I thought of trying to like go over that in a little bit more detail, and I create a few. Let me see if I have a few additional examples for that. But before I get to this, let me go back to this, which we have already seen, but just like to refresh the starting point. So if you remember, we had like a two-group comparison, and we were looking at activation, like a Speechman spatial activation in two groups of subjects, and we were looking at age as a covariate. And it was like an example of an unfortunate scenario where we didn't want to have like a age difference between the two groups that we were interested, but just because of sampling randomness, we end up having a difference between the two groups, right? So one of them was older than the first one, and we wanted to try to correct for that, like statistically. We say, well, this is really something that just happened because of our random sampling, and we really want to ask the question of what would be the difference between the two groups if they had actually the same age. So basically compare the activation in the two groups at the same age level. And this is what you do basically when you introduce age as a covariate in an ANCOVA type of analysis, right? So this is like an ANCOVA where you enter group A, group B, and age, and then you just look at group A minus group B and enter a 0 for age. And what you are actually doing is basically looking at the difference between the two groups at the same age level. So basically, instead of looking at the means of these distributions and comparing whether the activation is higher in the blue for the blue group guys versus the red group guys, you want to ask, well, at the same age level, so basically if I draw like a vertical line here, what would be the difference between the two groups if I compare them at the same age level? So basically correcting for that difference, and that kind of like makes sense. That is the typical use of a covariate as a control covariate when you want to control for something. And then we also saw these other samples that have not much to do, but this is a way to see what, at least in the ANCOVA literature, is presented as adjusted means. So basically, what if I want to know what is the activation level in this group at age 25? How would I ask that question? Is the activation at age 25 positive or not? And this is how you do it. Basically, you just select the group A, which is looking at the intersect of this white line, and then you center the age at the level that you want to investigate. So if you care about the age 25 and you want to ask the question of what is the activation of group A at that age level, you center your covariate age at level 25, which means basically subtracting 25 to all of the age values, and then just look at this contrast 1, 0, 0. And because this variable basically encodes the intercept of this regressor is going to encode the intercept of this kind of like a fit to the data at the age 25, that basically encodes the height of this line of this fit at that age level. And that's basically the question that you're asking here: what is the activation at that age level? And then we also look at this, basically, what if I want to do like a group by age interaction? Basically, I assume that the activation is changing with age, and the activation might be changing with age at a different rate in one group versus the other. And I want to evaluate whether that is actually the case or not. And I want to test whether the rate at which activation changes within one group is different than the rate at which the activation changes in the other group. How would I test that? And basically, you would enter this type of model where you enter both like two. Basically, this is the intersect for the group A, and this is age only for the group A and zeros for everybody else. And then this is a dummy coded covariate for group B. It's just ones for the group B subjects and zeros for everybody else. And then this is an age covariate, but only for group B. Basically, the age values for group B and 0 for the group A subjects. And then when you enter those four regressors, you're effectively trying to fit this data using this type of regression lines that they can have potentially different slopes across the two groups. And then you want to evaluate the y-intercept is going to be encoded by this group A, group B regressors, and the actual slope of these lines is going to be encoded by the HA and HB regressors. So if you want to evaluate whether the slope is different between the two groups, you just enter a contrast like this, like a 0, 0, 1, -1 to evaluate whether the slope, which is encoded by this in the first group, is different from the slope of which is encoded by this on the other group. This all makes sense so far?
Mm-hmm.
Cool. Okay, so to go one step back, one thing that I didn't mention the other day when we were talking about this is I mentioned like a simple regression when you do like a correlation between age and activation, right? But I didn't look like expand on that. How can you can also do the same thing, but in a context of like a multiple regression analysis. So instead of having just one single regression, you could have multiple regressors, right? And the question is, what happens in those models? What is it that we are testing? Because particularly when the regressors might be collinear, right? So they might be somehow related. They might not be orthogonal. So as an example, and this is going to be exactly the same as a model that we've seen before. Let's say that we think of this as a regression, and we are just entering, instead of all subjects and age, as we did before, to look at the correlation between age and activation across all the subjects, I want to enter an additional covariate. For example, I'm going to enter gender. And the point here also is to highlight that when you enter covariates in a regression model, it doesn't matter whether those covariates are actually like a binary measure like gender in this case, or they are actually like a continuous measure like age. They are all valid covariates to be entered into regression models. So basically these are a multiple regression model with two covariates. Just one happens to be gender, which is encoding like 0 for males and 1 for females, for example, and then this is just a continuous covariate age, which has basically the age level for every subject. And then if you evaluate a contrast like this, for example, and you are using a 0, 1, 0 contrast to look at the age effect, the question is, well, what is it that we are measuring here? When we look at the age effect, how does it play basically with the potential interplay between age and gender? So for example, in this example, we are assuming that, I don't know, males are these blue guys and females are these red dots. And it just happens that and age is this covariate. So in this example, males are older than females, right? And so this covariate, the covariate gender, which basically encodes 1s for males and 0 for females in this example, or vice versa, and the covariate age, which just encodes the x coordinate of all of these dots, they are correlated. They are not totally orthogonal. So when you are testing something like this contrast, what is it that you're measuring? And it's relatively simple. In all of the multiple regression analysis, when you have multiple covariates and you evaluate the effect of for each one of them, you are always evaluating the what is called the unique non-shared variance of that effect. So basically, what is the effect of that particular covariate after controlling for everything else? And this all comes down to the nature of the hypothesis testing framework. I don't know, this is going to be a little bit going back a long time, but when I talk about this GLM talk, I mentioned that all of this hypothesis testing was using the likelihood ratio test, and that basically general framework for a test simplifies to what we typically think of as a T statistic or an F statistic or a chi-square type of test. But they all come down to the same model, which is basically a likelihood ratio test, which is evaluating the difference in the likelihood of the data under one model, the full model, and the likelihood of the data under the reduced model or the null hypothesis model. And in this case, when you are using a contrast like this, basically you are comparing two models as well. You are comparing a fit to the data that happens when you model everything as you enter here, basically all subjects, age, and gender. So basically this type of fit that you could get to the data. And you are comparing that to another model where this effect that you are testing, so for example, the age effect is 0. So you will have a second model that is kind of like the null hypothesis model, where everything else is still in the model, but the age effect is removed. So basically you are forcing the age effect to be 0 and asking the question, how well can I fit the data when the age effect is actually 0? But anything in the age effect that is actually encoded by other covariates, anything that is collinear, because of in this example, for example, age is kind of collinear with gender. So that difference between the activation between these guys and these guys is still going to be modeled. So we're going to fit something like a horizontal line in here by these guys and a horizontal line around here by these other guys. So there is some portion of the difference that actually depends on age that is still modeled by this null hypothesis model. It's only the portion of the covariation between activation and age that is not already modeled by everything else, but in particular by gender in this case, is the thing that we are evaluating here in the hypothesis testing framework. And it's the thing that is giving us a p-value. So if this p-value is a low number, then it means that adding age on top of what was explained by everything else is a significant contribution to the fit. And if that p-value is high, then it means that adding age to that other model that doesn't have age but has still everything else is not a significant improvement of the fit level. And because of that, basically when we evaluate a contrast like this, we are always evaluating basically the unique contribution of age, the unique contribution on top of what is already or could already be potentially explained by the other covariates. Okay, does this make sense? I mean, conceptually, do you have any questions about this so far?
And is the point of that just that when you're evaluating that, you're getting the effective age, but the slopes or the lines, the fit lines are going to be calculated, are going to be the same, but in different placement on the x-axis or y. I mean,
right. So
different intersect. Yeah.
Right, so the effect of, basically when you are testing the effect of age is actually giving you the slope of these individual lines, but it's kind of controlled by gender because it's not giving you something like this black line in here that is, if you didn't know about, let's say that these were all the same subjects and they were not divided in two groups, and you try to find the correlation between activation and age, you would fit something like this black line, right? Right, without knowing anything else, that would be the slope that tells you the best kind of like fit between age and activation. But in this case, that is not what is happening here because it's not telling you the global correlation between age and activation. It's telling you the correlation between age and activation at a fixed gender level. So basically within males or within females, but not across all of the subjects, right? So any covariation between age and the groups, basically between gender, is kind of removed before computing these slopes. So instead of giving you this slope, it's giving you this kind of like within group slope. Does it make sense?
Would you mind just going back to the slide before? I just want to compare this to the top slide.
Right. So this actually and this
for a covariate.
So
it's the between subject contrast.
Right.
So, because if you had something like all subjects age group,
yep.
That's going to show you the effect of age that's like in both groups, right?
Right. So basically, this model, all subjects, age, gender, and this model, and let's say this is males, females, and age, are exactly the same models. You see that you actually get the same fit to the data. So the red and blue lines are the fit to the data that you get with this model. And it's exactly the same as the fit to the data that you get with this model, the all subjects, age, gender. It's only encoded different, the model, and that basically allows you to test things using different type of contrast, but the actual model is exactly the same. So for example, in this, if we wanted to look at that difference, basically the difference between the group males and females at a fixed age level, using this type of definition in this model, do you have a guess as to how you would specify that contrast? So basically specify this model, all subjects, age, and gender, and then you have to say which contrast you would use if I wanted to ask the question of what is the difference between males and females at some fixed level of age.
I would guess 001.
Yeah, and that would be perfect. That would be the exact guess. So basically, if you enter a 001, which is basically asking the question of the gender effect, it's actually evaluating that effect, the difference between this line and this line, which is exactly the same as entering this males, females, age, and then entering a 1 minus 1. The effect sizes, the t-statistics, the p-values, cluster statistics, everything will be exactly the same. It will be precisely the same model. There are no even minor differences between the two of them. There's just two ways to encode the same test, basically the same hypothesis testing. I just chose to do it in this way because I wanted to talk about like multiple regression. And when you do regression, you typically have like an all subjects and then your covariates. And I wanted to kind of like use that as a basic example that we already seen in a different perspective. But think of this particular model as a multiple regression model, and think of these two covariates as two like continuous covariates, or well, not continuous in this case, but two covariates in a typical multiple regression analysis. Does it make sense? Does that answer the question that you were asking, Jason, about the difference between this and the other model?
Yeah, effectively.
Okay. Okay, and the same thing could be asked here. Basically, the same the age effect that what we are evaluating here with a 0, 1, 0 contrast is exactly the same as what you would get in this model using a 001 contrast. If I want, that would basically tell me the slope of these lines, which is basically the same with what I'm asking here. What is the slope of these lines? And that H effect that we are measuring here is effectively controlled by gender because, well, from the multiple regression perspective, because when you evaluate one effect, you're always getting the unique contribution of that effect after controlling for everything else. And from a perspective of an ANCOVA type of analysis, because when you are evaluating the effect of H, you are doing that within groups. So basically, you are evaluating the slope of the association between activation and H within males and within females separately, basically. Does that make sense?
Sure.
Do you have any questions before moving on? Because I think I'm going to move to this, which is kind of like the slightly different thing. So this has to be relatively clear so far. This seems to be like, yeah, this sounds all obvious to me. I mean, there's no questions there. And this is going to be like the, wait for a second, why was that? Exactly like that. So far, everything looks clear and reasonable and kind of obvious to some extent.
Yeah.
This thing in and of itself it's fine. The top thing here.
Okay, cool. Okay, so the thing that I'm going to talk about here is basically something like this, but in some cases you don't want to, when you want to ask a question about age, you are going to find cases, and I think we already ran into that in the example that we were talking about the other day, where you don't want to do that. When you have like a multiple regression analysis, but you don't want to compute age basically at the same level of that covariate, like in this case, because in this case makes sense because the gender covariate, we are assuming that it was like a random sampling type of issue. It wasn't necessarily the case that gender was correlated with age. It just so happened in our sample, but that doesn't have anything to do with our way of conceptualizing the effect of all of these covariates with connectivity, but sorry, with activation. But in this case, there are some cases where that will not be the case. And the one simple example that might not be exactly what we were talking about before, but it's simple enough, I think, and it's general enough, is to think of a covariate that is health, basically, like a health indicator of general health status. So to some extent, I mean, this is an informative measure, right? And you want to know whether that correlates with activation or not. So basically, are healthy subjects better having higher activation or lower activation in some particular region? And you also want to see how that changes with age. So perhaps the activation in that region is going to change with age in a reasonable manner. But then you figure out, well, you know, age and health indicators are somehow correlated. And if this is like it's not like an IQ measure that is going to normalize for different age levels. Let's say that our health measure is like a global measure. It kind of like makes sense to expect that the older population are going to have in general lower health status than the younger population, or at least let's assume that that is the case. So there are perfectly reasonable reasons, sorry about that, to expect that these two things to be correlated beyond just sampling error. This is not an issue that we want to correct for. This is just something normal. We expect that older people are going to have generally lower health indicators than younger people. And we still want to estimate the effect of age and want to estimate the effect of health, or at least the relative effect of health. So how do we actually do that? Because in that case, we don't want to do something like this. We don't want to estimate let's say that we want to estimate something like this black line, right? We want to estimate the general effect of age, even though there might be something beyond that general effect of age that is explained by the additional covariates, instead of, in this case, health status. So how do you actually do that? It sounds like you have exactly the same scenario. You have exactly the same contrast, you are just changing the name, right? But why would that be different? And you are exactly changing the contrast in here. But now we want to estimate this global effect of age without controlling for health status. So we are not asking the question, what is the correlation between activation and age at the same health status level? We are asking the question of what is the general correlation between activation and age, taking into account the additional contribution that other effects like health have on activation, which are themselves correlated with age. And the way to do that is basically to orthogonalize this additional contrast. If you don't want to control for this additional contrast, so if you want to measure the effect of age, but without controlling for this, just taking into account that additional covariation, the additional effect that these other covariates have, but without making it a control covariate, then you basically orthogonalize that effect with respect of your covariate. So instead of entering health like a 0 or 1, In this example, I'm using exactly the same data just to highlight the differences. Typically, health will be a continuous measure, but let's assume that it's just like a 0 and a 1, and you have like to specify some cutoff for your health status covariate, and you say these are my healthy subjects and these are my not so healthy subjects. And they just so happen that you're going to have these which are relatively older, which are your not so healthy subjects, and these guys which are, in general, relatively younger, which are your more healthy subjects. And in the middle, you have a little bit of a mix. In this age range, you have a few subjects which are more healthy and a few subjects are less healthy. And in the extremes, you have only subjects that are less healthy. And here in the extremes, you only have subjects that are very healthy in this case. So this is kind of like the same data, but I just changed the gender to be basically health status. So how do you orthogonalize by that? But basically what you want to do is basically orthogonalize that covariate with respect of age. And orthogonalization is just actually that mathematical operation. You just remove from the health covariate, which is just some numbers, in this case zeros and ones, anything that can be explained by the other covariate, so by age. You try to fit a regression between age and health and remove whatever you can fit and just take the residuals. So in this case, you are going to end up with something like, imagine that, I don't have that very well plotting here, but imagine that you have like in the X, you have age, and then you have something like, for these guys, you have let's say these are the more healthy, so we are going to call it a 1 for these subjects, and these subjects have a 0. So you have something like age in here, and you have ones kind of like more at the left and zeros here more at the right, and you try to regress age, which is the X covariate. Basically, it's going to be a line like this. So when you remove that from the additional variable, you are going to have something that is like a relative effect of age, of health at a given age level. So instead of having like an absolute measure of health, you are getting a relative measure of health at that given age level. So relative to the health level that you would expect at that given age, what is the actual health level of each individual subject? Basically, that would be zeros for people who are in here, which are basically telling you that these guys are as healthy as you would expect. You will have like ones for these guys, the red guys around here, which is basically healthier than you would expect in general at this age level. You will have like minus ones or something like that for like negative values for these guys in here, which is basically telling you that these are less healthy than what you would expect by that age level. And then you will have again something around 0 for these guys in here, which is basically telling you that it's as healthy as you would expect at that particular age level. So instead of having like an absolute health covariate, you have a relative health covariate controlled by age. And when you enter that relative health covariate controlled by age, you get exactly the same fit eventually to the data, but now it's encoded differently. Now the age covariate is telling you this global slope, and the health orthogonalized covariate is encoding the difference between these two lines and that kind of like average line across all of the subjects. So basically, if this health orthogonalized ends up being 0, then that means that the best fit to the data is just that black line. If this health orthogonalized is positive, then basically you get this type of departure from that line. So in this particular case, the best fit to the data would be exactly the same as what we have here. This would be like this kind of like semi-transparent line. It's only that the age covariate, that is what we are testing here, is actually giving you the slope of these lines instead of the slope of these lines, which was what we were getting before. Okay, so how much sense that makes?
So can I ask a couple follow-up questions?
Sure, please do.
Okay, so I think, what you're saying is that this slope, depending on what the effect of age is on health, this slope could be positive, it could be negative, it could be in any orientation relative to this data set, correct?
Right, well, in this, well, continue, sorry.
Well, so with I was originally going to ask, so this line looks like the same as if you didn't have the health orthogonalized covariate at all, and you were just estimating the effect of age.
When you say this, I don't quite see where are you pointed. So you were referring to the blue, like semi-transparent.
The black line. Right? Yeah, the black line looks at what you would get as the effect of age if you just got rid of the health orthogonalized regressor altogether.
Yes, exactly. It is actually, yes. It is exactly what you would get with just correlating with age. Well, let me check.
But doesn't the model account for some of the variance accounted for by health status?
Right, exactly. I mean, the one thing is kind of like the slope, the meaning of that number, so the effect size of what you get with that contrast, and that is exactly the same as what you would get, basically the slope of how much activation changes with age as a global measure. But then the statistics are different. If you just enter a model that says all subjects and age without this covariate and just enter a contrast 0 and 1, then the statistics are going to be worse, basically, typically, than what you would get in this particular model when you are not, even though the effect size, the slope that you are testing is the same, you are testing it with less power because the thing that this model that only knows about subject and age knows about this data is it doesn't know that a lot of this variability is not just normal random sample variability from subject to subject. It's variability that could be explained by this additional covariate that you actually know for this individual subject. So when it estimates the effect of age and it tells you basically the confidence interval that it has on this slope being this size is different than the confidence interval that this slope is this size if you didn't inform the data, the model that this additional covariate could be explained by this additional, this additional variability could be explained in the data by this additional covariate. Does that make sense?
Yes, I think so. Just as a hypothetical, if for some reason the relationship between the effective age on health is different. Let's say that the older
subjects are more healthy.
Like the older subjects are more healthy. Right. So let's imagine that these blue guys are kind of like on top on here, or something like that, right? Or do you mean just on the? So, or change the status of which one is healthy and which one is not. What do you refer to?
Well, maybe let me ask this a different way. So it sounded like when you were explaining sort of what that black line was doing was connecting the 0 point in the well, I don't know actually, connecting the 0 point in the healthy group versus with the 0 point, or the zero point in the red group and the 0 point in the blue group, but because you've gotten rid of the effect of.
Oh, I see. But the 0 point, you mean kind of like the centroid of the distribution, or what do you mean? So something like what I'm highlighting here in the bottom, this kind of like dot in the bottom plot, or something else.
So you were mentioning that in the red group, the like lower left corner was, I forget in what context, but lower left corner was 0, and as you move up becomes -1. I don't know if that's the effective age. Right.
So if you think of the relative effect of health on subjects, basically I try to encode what is the relative health status of an individual subject, not in global terms, but in kind of relative terms. So basically for their same group level, age group level, what numbers you would assign. So you would say something like zeros for these guys because they are as healthy as you would expect on average for these people. These guys. Red because you take all of the subjects around this group level, some of them are healthy and some of them are not. So the ones that seem to be, so on average you get like average health like 0.5. So these guys that have 1 and the initial health variable are going to have positive values because they are above average, right? Within their age group. And these guys that have 0 in the original age covariate are going to be below average for their same age group. So they're going to have negative numbers. And then again, these guys in here at the age level, they are all going to have, so the original health covariate is going to be zeros for all of them. So they are going to be, and that's pretty much the average for that group level. So that again, all the subjects will get pretty much the same numbers or something around a 0 for those.
So, but I mean, I think we can spend forever on this, and I think this is the danger that we get into with these is that we can say, well, what about this? And we're spending a lot of time trying to connect this to like an example of something that we would do.
Yeah.
And I think that we're finding an inefficiency here, and maybe that's just me. Maybe it's that it's just hard for me to keep up with everything. Trying to figure out like how to connect this to what we're doing. And I don't know. I mean, I guess I'll just say that I'm not sure how much we get out of dialing this down before we take a step back and just try to make sure we
Right. Okay. If we just try to keep like kind of like the moral of all of
This
this.
is doing. But one thing that would really help me is if before every example there was a question, the question that that you're asking. What is the blah 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 effect of this controlling for this? Something like that.
Okay.
So for the second example, I think this might go at a question would be like, what is the effect of age controlling for health status, but not health status that is correlated with age?
Yes, that would be exactly the case in here. Basically, if you want to ask the question, what is the effect of age on activation, but not controlling for health status, basically the overall effect of age on activation, and you want to test it on this overall model, basically that it informs that a lot of the variabilities in activation actually depends on health status and not only on age. So you don't want to disregard that or make as if you didn't know that. You want the model to be informed about that, but you don't want to get the effect of age control at a given health status level. You want to get the overall effect of age, even though health is going to be correlated with age. So how do you actually test that? How do you test the effect of age on all subjects, informing the model about health status without controlling for health status? That would be kind of like the general question here.
So this is evaluating the total effect of age, like the total of including that's including the shared, like the joint effects that it shares with health.
But not health status, that is.
No, but actually encompassing the portion of that difference that actually is explained by health. So yes, without controlling for health status. So for example, let me see, how can I?
Well, I mean, it seems that if age and health status are correlated, then there's probably some amount of variance accounted for by age, some amount of variance accounted for by health status, and some that's shared.
Yeah, exactly. And this is the typical thing that I was showing above, is that when you test in a multiple regression model, something like that, where you have like two covariates and all of them, some of the, it's going to be like in a Venn diagram type of thing. You have some portion of the outcome, which in this case is activation, that is explained by the first covariate, and some portion that is explained the second, and some portion that is explained by both. When you are testing the effect of one single covariate, what is it that you're actually testing in this kind of Venn diagram? You're always testing what is called the unique variance. So you're always testing the effect of one covariate after removing anything that is already explained by the other one. So in that Venn diagram, you are actually trying to evaluate the model that is explained by this covariate, but removing the thing that is in the intersection, because that could also be explained by the other covariate. That is the typical thing that you would do in the upper type of test when you are wanting to evaluate the effect of one covariate after controlling for everything else. So basically discounting any portion of the outcome that is already explained by potentially by any of the other covariates. And in the thing in the middle, in this example in the middle, you don't want to do that. You want to like say, well, okay, we have some amount of intersection between this covariate and this other one. I want to evaluate the entire circle, the left circle of even though some portion of it is going to be intersecting with the right circle. So what you do is basically orthogonalize the covariate. So the right covariate, the covariate in the right, is not actually explaining any portion that is in the intersection. It's only going to be explaining whatever is not in the intersection. And in that way, when you evaluate the covariate in the left, you are actually testing the entire circle instead of only the portion of the circle that is not a part of the intersection. Does that make a little bit more sense, perhaps?
Yeah, a little bit.
What's the circle?
So the circle is the amount of variance in the outcome, in this case, in activation, that you are explaining by each variable. So imagine like just two circles intersecting. The space that you're looking at is the actual activation, the space of activation. The circle is the portion of the activation that you are explaining by one covariate, and the other circle is the portion of the activation that you are explaining by the other covariate. And there is some portion that is shared, that is actually explained by either one of the, by the two of them, right? And that is the intersection between the two circles. Does that make sense?
The circles are not related to the data points here. They're just
Oh, right. This is just a way to look at regression models. Like it's called the Venn diagram, and it's just a way to think about regression. The space is supposed to be the space of the outcome variable, kind of like the total. Imagine like the page is actually total variability in activation that is in the data. You are never going to explain all of that with one covariate, like age, for example. You're going to explain a portion of it. So then that you draw it like a region that is the portion of the entire variability that is explained by this covariate. And then you have another region, which is the portion of the entire activation set that is explained by this other covariate. And those two regions may intersect because some portion of the space of the activation, basically the variability across subjects in activation, could be explained potentially by either of the two covariates. That's kind of like the intersection of the two areas that you are plotting. Makes sense? Perhaps I should actually create those plots and put them in here as part of the explanation, because that actually might be helpful for people who are a little bit more familiar with this. Like,
I think that would be helpful.
yeah,
Say, like, you know,
yeah, because
the diagram explanation is good.
yeah, and that also kind of highlights the difference in here, because that, like, kind of the moral of the story is entirely that. Basically, the difference between the top plot and the middle plot is basically that in the top plot, in that model, we are trying to test what is called the unique variance, and that's the portion that is not in the intersection in this Venn diagram. And in the thing in the middle, you are trying to evaluate the size of one circle, whether it's actually intersecting some portion of it with the other covariate or not. So it's a way, it's kind of like a trick to evaluate the size of an entire circle instead of evaluating the size of the portion that doesn't intersect with anything else, with the other circles.
Just evaluating.
That's the top.
Age. This is the whole thing.
Yeah. And then
then
the second one
the
is
second
it's
one,
the whole thing.
It's the whole thing.
Just put those Venn diagrams in there.
Yeah.
Yeah, I should. That's a good point. Yeah, and well, I mean, this takes a little practice, but this thing is basically it comes up all the time. I mean, when you have multiple covariates, at least when you have multiple things that you are trying to inform your model about, you might have, like, I don't know, age, gender, IQ, SES, a lot of things that you just think of control covariates, but then some of them are things that you are interested in actually finding the covariation between these and the activation, but then some of them are going to be correlated between them because the covariates are never, like, totally independent, or there is always a certain amount of collinearity between the covariates that you are using in your regression models. So this kind of like comes up in pretty much every scenario that you are using
In
multiple.
this case, you need to orthogonalize the covariate before you.
Yeah, exactly. So the trick is to orthogonalize the covariate before actually entering into the model.
To do that, you're running just a simple regression between age and health or health status, and then pulling out the residuals and using that as health or job.
Exactly. Yeah.
It seems like there might be a way to do that in one. Is there a way to do that in one step? If you're running, say, I don't know, some stats package, but the framework here requires you to do that. I mean, it's not it seems like it makes it easier to sort of wrap your head around what's going on if it's done this way. But is it just the framework here that we're using that requires that orthogonalization first, rather than trying to, like, you run like some great big, you run like some test on, you just input all the data and then you pull out the pieces.
Right. I mean, many statistical packages, like, I don't know, SPSS and this type of thing, they basically gives you like a long list of, when you like run a regression like this, basically they give you a long list of outputs, and some of them are going to tell you basically the unique variance, and some of them are going to tell you the shared variance, and it's up to you kind of like to know what all of these output variables mean, and to get the one that you actually care about. But in this case, where we just want to typically just run analysis and get one statistical image instead of like 20 of them, and for you to have to pick up which one is the one that you actually cared about, I think it makes more sense to basically do that orthogonalization manually. I mean, I could easily have the FL scripts to actually encode this type of orthogonalization in a meaningful or simple way, so that you don't have to actually kind of outside of everything compute that orthogonalized covariate. Just have a way to encode that I want to orthogonalize this covariate with respect of this other covariate or something like that. But it's general, in the kind of like general scenario, you need to be able to orthogonalize individual covariates against any potential subset of other potential covariates. So it can get complex, basically. But I don't know, I could encode, allow RFL kind of like design definitions to have some keyword like orthogonalize or something like that. That instead of entering health, you enter orth health age, for example, and that means health orthogonalized by age, or there are scripts to actually do that for you.
That seems reasonable. That seems like if we I don't know exactly. I don't think this has come up necessarily, so I don't know. Well, but it might be good to have some easy way of doing it. If it did
I
come
don't
up.
think it would have come up because I don't know that any of us
Would have thought.
thought that this was
This was
just something that we would have
Right,
wanted.
sure.
or that what we're actually asking for is this,
Right.
right?
Right.
Yeah.
So I think that we go through an example. So we talk about things like we want to remove the effect of motion. But we also want to look at we want to look at like a correlation with motion. But we want to just remove that effect.
Yeah.
Then when we start talking about things that are more like central to severity of
Right.
symptoms, something like that. It may be that just thinking of it this way, this makes it much easier for us to communicate with
that's true.
Alfonso and
Yeah.
Frank in terms of like what we're trying to accomplish. So I think Alfonso, I don't know. Let's
Continue.
yeah, when we get to some real world examples, we can see when this comes back.
Right. I mean, all of this is kind of like to try to give you kind of the general framework to think about these issues, basically. But yeah, I mean, in practice, you have to basically run into these issues and to basically more directly understand basically where the difficulties. But this kind of like I mean, all of this that I'm explaining here is not totally because I thought it was cool to talk about that. It was because of the whole symptom thing, because the plot in the bottom, because this symptom, the issue that we were talking about the other day about, well, perhaps the things like severity, and they're actually correlated with my groups, but that makes sense because I expect my patients to have higher severity in stuttering than my controls, and that's perfectly fine. I mean, how do you ask the question of what is the difference between the groups? I want to inform about severity, but without actually controlling for it, or whether I want to actually control for it. This is basically to give you the tools to think about that question in the most general scenarios. And the most general scenarios is this kind of like multiple regression, because this whole thing that I was talking about, we were thinking of it in a context of an ANCOVA. Is actually an ANCOVA is no different. That's why I show it in this example as a general multiple regression. And the way to think about this centering that it was all confusing about why to center one particular symptom score is because centering is just a form of orthogonalization. So this whole thing that I'm talking about, how do you orthogonalize one covariate versus the other one when you don't want to control for it, is just trying to give you basically the tools to think about all of these issues in general. And if you want, I can go with this particular symptom score type of thing that we were talking about in terms of like the severity, I think, instead of symptoms, but it was kind of like the same idea. What if we have something like this, for example, that we have two groups and we have something like severity and calling it symptom scores, but it's just the same. And you are saying, well, this particular group is actually now this covariate is not age. Let's think of them as severity score. And it's perfectly fine that this group has higher severity than this other group, because that's part of the group definition, right? I define my groups to be like the stuttering group, which has higher severity. I expect them to have higher severity, and then the non-stuttering group, which is I expect that to have lower severity in whatever measure I'm using of severity. So what if I want to, but I actually find that severity actually correlates with activation in one particular region, because it just so happened that the more severe, and that is going to happen within patients and within controls, right, within the two groups. So the question is, how would I ask the question of what is the difference between inactivation between patients and controls, informing the model about the actual whatever variability in activation is actually explained by severity? That is perfectly fine. I want the model to know about it, but I don't want to control for it. I don't want to ask the question, what is the difference in activation between patients and control at the same severity level? I don't want to ask that question. I want to know what is the global difference in activation between patients and controls. I know that some portion of that difference is going to be correlated with severity. That's fine. I just want that model to tell me the difference between patients and controls in activation, the global difference. But I want that model to also be informed that some portion of the variability is just explained by severity. Beyond the variability that can be explained by the difference in the groups, some additional variability in activation is going to be explained by severity. So how would you ask that question? And you think of that question in the context of the multiple regression models that I was talking about before. You would ask it as not exactly this example that I showed here, but you would ask it as something like where you would enter group A, group B, and then a severity symptom score across all of the subjects. But now you want to ask the question, let's say, imagine group A, group B, and just one single symptom scores, and you enter a 1, -1, 0. But then how do you make this not to be controlled by symptom scores? By orthogonalizing the symptom score against the other covariates. So basically, you will have to orthogonalize symptom score against the group A and group B covariates. That's what we were doing here, right? Orthogonalizing health against age. So in this case, it's the same. If I want to find this effect without being controlled by this, I need to orthogonalize this variable against these effects. So basically, orthogonalizing the severity score against the group A, the dummy-coded group A and group B covariate is basically the same as centering. When you orthogonalize against a covariate that just has ones and zeros, you're basically removing the average of that covariate. And you are doing that separately for the two groups, right? So remember when I talked the other day about how you would do that by centering the severity score separately within the two groups and making the zero mean the zero value of the severity scores within one group to be the same value, to be basically the average of the severity scores within one group to be 0, and the average of the severity scores across the other group to be 0. And if you enter that symptom score here and just test the 1, -1, 0 contrast, you're actually asking that question. What is the difference, the global difference in activation between the two groups? Without controlling for symptom, but still having the model informed that some additional portion of the covariate beyond that difference between the groups is going to be explained by the severity score. Does that make sense?
Yes. Yeah. I have just a small follow-up question.
Sure.
If you were to make symptom A, Sympt A and Sympt B into one variable, but for group A, the subjects, if you separately centered each group and then just put them all in the same variable, would that do the same thing? So let's say
if you have something like all subjects and group and symptoms, you mean?
Yeah.
Right. Yeah, that's perfectly fine. You could just orthogonalize the symptom against the group covariate, and that will work perfectly fine. The implicit orthogonalization between the symptom and the all subjects covariate is just removing the mean across all subjects, and that doesn't quite matter. So that's just fine.
Well, I mean, I guess I was actually asking a slightly different question. So let's say your between subjects effects were group A, group B, and then Sympt. If you just had one covariate. If for, let's say, subjects 1 through 10 are in group A, subjects 11 through 20 are in group B. Mm-hmm. If you centered each of those values within group and put them in the same, so would that do the same thing?
Yes, that's exactly the same. And that is actually what you would get if you orthogonalize the symptom score across the two dummy-coded covariates, the group A and group B. So basically, if you try to fit symptom scores using one regressor that actually just encodes 1 for group A and zeros for group B, then basically the best fit to that data would be the average of the group A symptom scores for those subjects. And if you do the same thing for the group B, basically the best fit to that data would be the average of the symptom scores, of the severity scores for that subject. So when you are computing the residuals, you're basically removing that average, which is the best fit, and the residuals are actually the effect of centering that covariate. So basically you are centering that covariate because centering is just orthogonalization against dummy-coded covariates. So basically, all of this scenario was to try to justify why it gives you at least a general framework to think about why that particular trick that I was telling you about, which is basically center them separately within the two groups, actually work, and how that works in a more general context. In a more general context, this is just like a multiple regression type of analysis, and the centering is just a form of orthogonalization. And orthogonalization works to differentiate between asking the question about unique effects of one covariate and shared effects between one covariate and something else. That's kind of like the general framework to think about all of this.
Gotcha.
Make sense?
Yep.
Okay, so that's all I had for that. We can come back to this when we have more examples. I mean, if you, again, the other day I asked you if you could send me like an example or something that you think it might make a little bit more sense for these explanations. If you can come up with an example or something, just feel free to send me an email and I'll be happy to kind of try to reconstruct that for that particular example. So it helps us think about all of this in more concrete terms, if you want.
I have an example. Well, I have I want to figure out the best way to create, like, to create the design for a specific situation that I'm dealing with. If we had more like general stuff, we could go over that, but I also have something specific that I want to get feedback and or what.
So what do you want to do? I can go about to talk about this is not very long. This is just talking about the like what do you have when you have multiple conditions? I mean, in the context of everything that we talk about, how do you specify the second level analysis? And
I think that
this is kind of like more theoretical, or we can go for examples and rest a bit about so much theory.
We
And
should go
general
through the multiple conditions thing at some point.
Yeah.
That could be now or it could be after the example.
I
It
think we
could be
should
a
go through
different
it
meeting.
because I think the example will have.
Yeah, does your example include multiple conditions?
Yes.
Then let's do this.
Okay, then let's do that first. Okay, the multiple conditions is really very simple. It's all, remember how when we talk about the multiple like factorial design, and this was all kind of like between subjects factors, right? So we were thinking about like different groups, but you have two factors. It was control versus patients and medication versus non-medication. And you can always specify, if you want to ask one particular question, you can always break it down into what that particular question is for one factor and what that particular question is for the other factor. So in this example is, what do I care about the difference between controls and patients? Do I care about the difference or about the average effect? And once you ask that question is, what do I care about the difference between medicated and non-medicated subjects? Do I care about the difference or about the average or about something else? And if you can answer that question separately, then you can just compute the Kronecker product for those two vectors or matrices that you could form for evaluating those contrasts separately on each individual factor, and that will give you the overall contrast vector or matrix that you will need to use for this particular example. So the moral of this is that the questions that you ask to your data through the hypothesis testing are always breakable into simpler questions. And if you can answer the simpler questions about the individual factors in this case, you can just reconstruct the contrast vector or how you specify the more complex question just as a combination of those individual factors. Well, with multiple conditions, it works exactly the same way. Basically, you can always think about your question, at least in the context of GLM, as separately asking the question of what do I care across subjects and what do I care within subjects. And across subjects is everything that we've talked about now, right? We talk about we were always thinking of activation as being like a speech minus baseline type of activation. But that's because that was our raw data. And we thought about, well, what do we care about in terms of that activation level across subjects? We could care about that we might have multiple subject groups, or we might care about covariates like age, or we might care about control things like motion, and but all of those are subject effects, right? Are things that change across subjects. So you can always ask the question of what do you care about across subjects, and then what do you care about within subjects? And within subjects, instead of just saying, well, we care about this particular speech minus baseline contrast, you can care about one or any combination of individual contrasts in the same way that we constructed contrast across the effects that we were modeling across subjects. We can always construct constructs across the variables that we are measuring within subjects. So if we have a subject, for example, that has a pre and post design for pre-intervention and post-intervention, or we have, I don't know, like fast and slow production of speech or whatever, like different conditions, you can always think of those things as within subject factors, right? And so you have a factor that is like the speed of speech, and you have two levels, that is pre and post. And that should be very similar to the factorial design that we were thinking about in terms of groups, but instead of looking at the variability across subjects, we are now thinking about variability within subjects. So we are thinking of, well, across all of these different conditions that we are testing for each individual subject, so these are actually repeated measures, what is the thing that I care about in terms of those factors or those effects? So for example, if you just care about the difference between pre and post intervention, then you just specify the two conditions that you care about and enter a contrast -1, and that would be asking the question about what do you care about in terms of the conditions themselves. And then on top of that question, you can just ask, well, I care about this across conditions, and what do I care across subjects? And you can look at the same thing across conditions and have everything that we have talked about before for a speech minus baseline contrast. You can think of them as you can apply exactly the same type of models for something that is looking at a difference between conditions. So if you have like a pre minus post design, or you have like a fast minus slow contrast, you can ask the same questions that we ask about is that difference, what is the average of that difference? Instead of looking at what is the average of activation, we are looking at now what is the average of that difference in activation between the two conditions across all subjects. So that would actually be like a PERT test, right? Where you have two repeated measures for a subject, and you have and you just look at the difference between those two and do a one sample t-test. So this is just like the beauty of the math behind all of this, is that a per t-test is just exactly the same as computing first the difference between those two conditions and then performing a one sample t-test. And that also works out because in terms of the contrast specification, the entire contrast that you need to specify to GLM can be broken down into what is the contrast that you care across subjects. In this case, I just care about all average across subjects, so I can just say all subjects in a one, because that's what I would do when I want to look at something across on average across all subjects. And then what is it that you care about across conditions or across your different contrasts? In this case, like fast minus slow or pre minus post, I care about the difference between these two conditions. So just select those two and enter a contrast that specifies the difference. And that would effectively be like a per t-test across those two conditions.
So Alfonso, just to clarify, so then in the plots here, what we're looking at is actually the different scores versus
Exactly. Yeah.
That's one single color.
Exactly. So now in the same thing that I was looking at here, basically the same thing that I had in here. Oops, sorry, I went too far. In this, no, not this one. In this plot, where I was just looking at the actual activation across subjects on average. So the y-axis was the actual speech activation. Now we are looking at the same thing, but we are looking at, instead of looking at the actual activation, we are looking at the difference between the two conditions. What is it? And for that particular difference in conditions, so for every dot is a subject, but instead of actually displaying the activation in those two conditions, we require like two dots. We are just plotting one single dot that actually encodes the difference in activation between the two. So this is the y-axis will be difference in activation between post and pre intervention, or difference in activation between fast and slow, and then the x-axis will be the same. In this case, like age. But for this particular model, we don't care about. But then the actual test is actually trying to estimate this average and giving you some confidence intervals around that. But now that average is not the average of activation; it's the average of the difference in activation between two conditions. Make sense? But the math is exactly the same. And what if you actually have the question of, well, what if this difference in activation between the two conditions is correlated with age? So now you're not asking the question of whether the actual activation itself is correlated with age. You're not saying the activation within this region is just getting higher or lower. I mean, as the subjects get older, or well, if get younger, if they can. You are asking the question, is not the actual activation itself what is correlated. You're asking the question, is the difference in activation between these two conditions what is actually changing with age? Perhaps it's, for the younger people, there is no difference in activation between these two conditions, and for the older people, there is a difference in activation. So this, I mean, you can think of, sometimes you think of this as an interaction, right? You could think of that as an interaction of the, I don't know, if you are thinking of the two conditions are the speed of the speech production, for example, you could think of this as an interaction between production speed and age, and that interaction is basically encoding whether the difference in activation between the fast and slow is actually difference in younger compared to older people, right? That would be like an interaction. And one way of think of that would be two-way ANOVA analysis. Well, like a well, let's think of, yeah, it will be like this is not ANOVA because a continuous variable, but in a way, it will be like you have two factors. One of them is age, that is a between subject factors, and one of them is speed, which is a within subject factor. And you are actually looking at the interaction between those two factors. Certainly, that is like a mixed interaction because you are looking at the interaction between within subject effects and between subject effects. But well, that interaction. You can also, that's again, the kind of like the beauty of the math behind all of this GLM is that it can be broken down into two separate questions, or at least framing that particular interaction is basically saying, well, what do you care within subjects? Within subjects, you care about the difference between fast and slow, right? Because that is kind of like what I care about. I care about whether the difference in fast and slow is actually difference between subjects in older and younger population. So if somebody asks me the question, what do I care about in terms of the within subject factor, I care about the difference between the two. So I could just specify pre and post, or fast and slow, and a -1 contrast to say, I care about that difference. And what do you care about across subjects, basically? And I care about across subjects, whether that is changing with age. So basically, that would be like a correlation with age. And we know already how to do that, right? It's like an all subjects in age and a 0-1 to look at the correlation with age. But now, instead of actually looking at the correlation with age in activation itself, we are looking at the correlation with age in activation differences between the two conditions. So all of those are equivalent manners of thinking about this thing, equivalent in the sense that they would actually effectively implement the same statistical model, and you will get you the same statistical statistics, no matter whether you use like this type of ANCOVA or like a mix between within subject design, or you actually pre-compute the difference between those two conditions and enter them into a correlation analysis, or just enter a GLM with this type of contrast, like two subject effects and two condition effects, and this 0, 1 and -1 contrast. All of those ways of specifying this question, they will give you exactly the same statistics and the same model because they are all effectively the same. Okay, so far so good. And it works basically for everything. I'm not going to go repeating pretty much everything that I already talked in the context of the speech managed activation, but I'm just going to like briefly say that everything that we talked about before in the context of the speech managed baseline activation, you can think of them in terms of more complex contrasts within conditions. Those are just answering the question of what do we care about in terms of the subject effects of the across subjects. Beyond that question, you can, on top of whatever answer you give to that, I mean, you could say that I care about correlation with age. You can say that I care about the difference between the groups when controlling for age. You can answer that in all of the different ways that you can answer that in terms of these multiple factorial designs across subjects. All of those work exactly the same. You can still apply the same models. You only have to specify, in addition to that, what do you care about within subjects. I mean, within subjects, you can do pretty much the same thing that you can do across subjects. I just talk about one particular example of like -1, 1 across these two contrasts, but you can actually use any type of within subject designs as well. Let's say, for example, that you have like 3 time points. So you have activation and you have like a longitudinal study, right, where you have like subjects scanned 3 times, and you are getting some. Well, I'm going to forget about what we have in this particular example across subjects. But let's say that you have subjects just scanned 3 times, so you have 3 measures per subject, and you want to ask the question of whether there are any difference in activation across those 3 time points. How would you ask that question? Just within subjects. I'm not going to care about what do I care across subjects. I'm going to just answer the question of what do I care within subjects if I just want to test whether there are any difference at all between those 3 time points. So that works out in pretty much exactly the same way as you had when you had like 3 subject groups. Remember, like when you have 3 groups across subjects, you would enter a contrast like this, 1 -1 0 0 1 -1, to test whether there are any difference in activation across those 3 subject groups. Well, exactly the same works within subjects. If you have these 3 conditions, you have 3 measures like time 1, time 2, and time 3, and you want to evaluate whether there are within subjects whether there are any difference in activation across time, you can evaluate with a contrast that looks like a 1 -1 0 0 1 -1. And on top of that, then you have to answer also the question to fully specify your model and okay, this is what I care about within subjects. What do I care about across subjects? And that can be answered in any meaningful way. You can say, well, I care about the activation across all subjects on average. Then you would just enter here like on all subjects and 1. Or you might have 2 subject groups and say, well, I care about the activation on average across the 2 subject groups. So you could enter like group A, group B, and 0.5, 0.5. Or you could say, well, I care about that difference across time, but I don't care on average whether that is changing across time. I want to know whether it's changing across time in a way that is different in my patients compared to my controls. So now you're asking the same question within subjects, but now across subjects, you're asking a different question. You're asking about the difference between patients and controls. So you just specify the same contrast within subjects, and then across subjects, you specify group A and group B and enter a 1 -1 contrast. And that's the way to evaluate that type of interaction effect, right? You're asking the question of whether the change across time, across these 3 measures that I have for every subject, is itself different in patients versus controls. So that will be really this type of mixed ANOVA design where you have like two factors. One is the between subject factor, this is the patients versus controls, for example. And then you have one within subject factor, which will be the time, basically the 3 levels, 3 longitudinal measures. And you are looking at the interaction of time by group, right? The group by time interaction will be effectively tested using this model. Group A, group B, 1 -1 across subjects, and time 1, time 2, time 3, 1 -1 0 0 1 -1 contrast within subjects. Does that make sense? Or this is getting a little bit too abstract?
Is this essentially like a linear mixed effects model thing, or is it similar to that?
It's similar to that. There is linear mixed effect models are a little bit different. They have like they have slightly different things. This is more like well, depending. I mean, the nomenclature. This is called like a mix within between subject factorial model. So basically an ANOVA with two factors, but it's sometimes called like a mix within between subject ANOVA, because one of the factors is a within subject factor and one of the factors is a between subject factor. So it's called a mix within between, but it's not the same as what people call mixed linear models. Mixed linear is something else, basically.
I think one thing that is just, I guess, maybe becoming clearer to me today is that for the between subject effects and the conditions, that's really where you're building your model and saying everything that we care about, you know, these are my between subject factors, these are my within subject factors. And then what you specify on the contrast lines is very much the effect that you're looking at in this specific analysis. So whether it's a main effect or an interaction effect that you want to pull out. Is that correct, Alfonso?
Yes, that is actually the case. Basically, remember when we were talking about GLM matrix, you have to specify four things, which is basically what are the columns of your Y matrix, basically what data you are entering into your model. That's basically the conditions that we are entering here, which is your actual data. Then you specify what are the contrasts of your design matrix. That's basically what are you modeling across subjects. These are the things that you specify here. And then on top of that, you have to specify those two contrasts. What is the contrast across the columns of Y, basically across the conditions, or basically things that you are entering in the data. What contrast do you care about that in terms of testing this hypothesis, whether some particular contrast is going to be zero or not. And this is where you specify the within subject contrast. And then you do the same thing across the columns of the design matrix. You already defined what was the model that you were defining in terms of all the subject effects. You have to specify which particular contrast you care about in that particular model, which you want to evaluate whether it's actually zero or not. And that's where you specify the between subject contrast vector matrix, right?
Okay, and then so if you had, like, let's say you want to run like a multiple regression where you're interested in more than one main effect, you run like each effect as a separate analysis. So let's say you want to look at the effect of age and then you want to look at the effect of severity. You don't ever look at them, assuming you want to look at just the effect by itself, you wouldn't specify, you might specify them both in a model, but you know, you're 0, 1, 0, it would be like 0, 1, 0, and then you run a separate model that would be 0, 0, 1.
Right, exactly. So the way that we are phrasing all of this and we are making the FL scripts work is that basically for every question, basically every hypothesis testing that you want to run, you have to specify these four things. Basically, you specify the entire model that you want to use, specify the whole data that you want to use, and then specify the actual contrast. So if you want to ask a different question about the same model, you would still have to run a different analysis, basically, entering the same between subject effects and perhaps the same conditions, but a different contrast across those conditions. Does that answer the question? What was the question?
Yeah, and that makes a lot of sense. And I think part of the difficulty is just coming from thinking in a different statistical framework and then moving into this framework and just trying to map, okay, if I wanted to do it this way previously, how do I now translate it into this kind of thinking?
Right.
So kind of as like an intro to all of this, I think there's some background information there might be helpful.
I think one thing that might, I was just thinking about this. So like your first level analysis, you get a beta for each regressor, and then the contrast, the speech minus baseline, is doing exactly what these contrasts are doing here with each of those beta regressors. So when you have so you just have to specify each contrast separately.
Right. Right, but then you can also enter multiple contrasts into your analysis, because that's kind of like the trick of, I mean, that the whole like GLM framework is that you can break this type of GLM analysis into two stages, and that's kind of like there is a paper by this Penny, the SPM group, basically talking about that. Basically, if you have this type of GLM model, you can always break it down into two steps. The first step is where you build the contrast, the first level contrast, and then the second step where you enter those contrasts into a second level analysis. So when you have like for example, a model like this, and you run a GLM on that, it's exactly equivalent to do these two things. You could enter these three things as the columns of your Y data matrix and enter this contrast, or alternatively, you could have specified this contrast, the 1 minus 1 You could have specified just the difference. The difference in the, well, let's use this other example. I could just use these two, enter these two contrasts, two columns, basically 2 data points to my repeated measure model and enter this contrast, or I could pre-compute that contrast within subjects and then enter those resulting contrast images into a one simple second level analysis where we have only one single measure here and one contrast here and the same second level model here. So basically the answer is yes, you can always break it down and specify the within subject contrast like a priori, but sometimes you don't want to be that level of explicit, right? And cover all potential ways of contrast. You can actually, it's a little bit redundant, but you can also specify the within subject contrast in this particular model, at the second level model, and that gives you the additional flexibility of entering particularly multiple sets of contrast into the same analysis, where you want to do something like this, for example, when you want to look at the difference between the conditions, but those are more than 2, there are 3, it would be a little bit difficult to actually pre-compute all of the contrasts that you would need to actually enter those contrasts into your second level analysis. It's just simpler to actually compute one contrast that gives you time 1, one contrast that gives you time 2, and one contrast that gives you time 3 within subjects, and then let the second level model to specify which particular combination you care about in this particular analysis. Make sense? But you're totally right that those are perfectly equivalent. If you could have totally gotten those contrasts, specify them at the first level contrast estimation step, and then specify a simpler second level analysis that doesn't have to care about those multiple contrasts or at that particular, create those combinations at the second level model. Was that the question?
Just to build on that a bit, in the past we've really dealt with we kind of just mainly stuck with whatever contrast we defined at the first level. That's what we can like test at the second level for the group. Now we're adding some flexibility here, and so it seems like at least in the configuration files that I've seen, people are doing something like speech minus baseline, and you just between condition contrast there's just one, and then you're looking at whatever. And then, but if you want to look at, say, like, if you want to look at, say, fast speech, like a fast speech condition and a clear speech condition, you might have fast minus baseline and clear minus baseline. Then you can test these sort of things. Is there any difference in the groups? Would it be? I'm guessing that it's mathematically equivalent for us to use the effect of fast minus baseline and speech minus and clear minus baseline as the conditions rather than the beta that we get, I guess the combined average beta that we get for each subject for just fast and for just clear.
Right. So yes, if you care about, so at the first level model, you could have specified a contrast that says yes, fast minus baseline and then slow minus baseline. And then at the second level model, you specify select the contrast, the fast minus baseline, the slow minus baseline, and enter a 1 minus 1 contrast to look at the difference between the fast and the slow. And that would be exactly equivalent as if in the first level model you have an additional contrast in addition to the fast minus baseline and slow minus baseline. You also define a contrast that says fast minus slow. And then at the second level model, you just select the fast minus slow contrast and enter a 1 for that particular contrast. Those two ways of specifying the model will be exactly equivalent. There is no difference at all between the two of them. It just makes it a little bit simpler not to have to specify the contrast a priori at the first level model. So basically at the first level model, when you run the first level analysis, typically define every contrast, like the basic building blocks of any particular contrast that you might care about, and then let the second level analysis specify which particular combination of those things it actually cares about that particular model.
Right. I mean, it seems like that's what we're going toward. I guess Saul and I talked about this a bit the other day. For some contrasts, you might want to just be able to look within a subject and say, do you see some effect here at the individual? So you can maybe look at the variability at that level.
And definitely looking at speech minus baseline is helpful at the individual level, just to be sure you can
Right. Right. So I know that some, I think it's FSL, at least at one point, their way they did analysis is that they didn't really use a baseline, right? Something like that, Afonso? So I could put a pin in this discussion, but I'm just wondering about whether or not we need to actually define a contrast. at the first level at all. Or if you just look at the betas associated with speech,
Right.
you
Well,
remove and you can.
yeah. I mean, you could potentially, but I mean, it's mostly a practical question. I mean, I think what typically works best is that there is some level of summarization that happens at the contrast level that I think you always want to have that level. And that level is basically when you aggregate across runs. So basically the main difference between the betas and the contrast vectors that we get, at least even if you just look at a contrast that just looks at baseline effect or something like that, is that it's always aggregated across all of the runs. If you have like multiple sessions or multiple runs for a given subject, the contrast vectors are always aggregated, while you, in the betas, you actually get a beta for every session. So at least that minimal level of contrast specification is useful, because otherwise you would have to enter all of the betas for each individual run and then aggregate them at the second level analysis, and that's kind of like overdoing it. Just you will have to do that pretty much every time, because there is almost never in a scenario where you don't want to do that aggregation. So I think that is kind of like the minimal aggregation that is useful. And then the rest, it just depends. I mean, if you find it simpler to actually create a minimal set of contrasts, as long as that is like fully defines everything that you care about, and then let the combinations to be worried about at the second level analysis, that works perfectly fine. Some other people might prefer to actually be as explicit as possible, listing all possible first level contrasts at the individual subject level, just for what you were saying, just to get those images for the individual subject as well, and to be able to potentially, I mean, evaluate their significance and things like that for individual subject analysis, even though those might not be that trustworthy. But anyway, so it's just a matter of preference at that point. But at least the minimal thing of just creating those contrasts of the building blocks of everything that you care about in that individual analysis, I think it's useful, because it allows you to do that aggregation across all the runs and all of the sessions, which you're going to want to have that anyway in pretty much every scenario.
Got it.
There are some kind of like corner cases scenarios where you actually don't want to do that, and you want to do, like, for example, in the, this subject-specific analysis that I develop a toolbox to do that allows you to do this type of cross-validation across runs. So, for example, sometimes you want to if you have like 10 runs, like 10 repetitions of the same design for one particular subject, you might want to use like a few of those runs to build like a localizer, and then use the other runs to actually estimate the data from that localizer. And you can do cross-validation to mix up which ones are the runs that are used to effectively estimate the localizer, and which ones are the runs that are used to actually estimate the effect sizes. And in those cases, you don't want to aggregate across all of the runs, because you want to look at run-specific, session-specific type of effects, so that you can do all of these interplay. But that's kind of like a little bit of a corner case. In most scenarios, we just want to aggregate across all of the runs. If we have 3 set runs, we consider them equivalent, and we just get the average speech minus baseline, or whatever, fast speech minus baseline effect across all of those runs, and we don't care about between run differences. So. And there are some codes actually in our FL pipeline that allows you to effectively do that as well. If you want to automatically create like session-specific effects, you can actually enter something that is called add session effects or something like that. There is a keyword for that will actually compute that. So if you estimate like a speech minus baseline and then add that keyword, it will, in addition to the speech minus baseline, it will give you like a speech minus baseline session 1, a speech minus baseline session 2, and so forth. So that you can actually automatically create all of those different session-specific effects without having to actually encode those as different contrast vectors in the speech minus in the first level analysis configuration files. Okay, and in terms of the well, I don't know if this is worth mentioning, because we might not get too much into any of these scenarios, or at least I don't think we have, but just last word on within subject designs. As we saw in the between subject designs, that you can have like a factorial type of model. You can have the same thing within subjects. So sometimes you have conditions that are not just a list of potential conditions, but they have some type of like multiple factorial design. So you could have like, I don't know, fast versus slow, and then you could have like a normal speech and I don't know, like speech under stress, and you have like 4 individual conditions, right? But they form like a 2x2 design within subjects. So you can the same thing that we saw like across subjects is basically translates exactly the same as the within subjects. If you have that type of design, you can always look at main effects within subjects and interactions or of the different factors within subjects, and it works exactly the same way as the contrast specification, as it worked across groups basically. So if you have those type of like a 2x2 factorial design within subjects, you would end up with 4 conditions, and you specify the contrast in this way. Like you end up with this like -1, -0.5, -0.5, 0.5, when you want to look at main effects, and you have this -1, 1, 1, -1 type of contrast when you want to look at interaction within subjects. So that's just like a last type of word for that type of like for the flexibility of this type of the type of thing that you could enter into the GLM model. So you can enter pretty much all of those type of things that we saw about. We saw about like a ANOVA test and regression and multiple regression analysis and this type of factorial designs and multiple regression. Well, I think I mentioned that. And the same thing that you can do across subjects, you pretty much can do also within subjects. And any combination of those things within subjects and between subjects gives you like a ridiculously large degree of flexibility for specifying very complex designs. There are some particular designs that are not covered by this GLM analysis, and as you want, at some point I can talk to you about which ones those are, but those are really corner cases. In most scenarios, you are going to be covered by this GLM analysis without having to do anything else, that is specifying these 4 things for every analysis that you want to run. So, Sol, do you want to go with your individual questions, or do you want me to? Do you guys have any particular questions about all of these, or things that you want me to talk about?
We're ready for a sample.
Yeah.
Okay, cool.
This is sort of I think I brought this up last time, but maybe if I share my screen.
Yeah, let me stop sharing mine for 1 second.
So, okay. So I basically, the rhythm study, I extracted a bunch of behavioral data from that. The one I want to talk about here is the mean speaking rate. So this is syllables per second on the y-axis, and on the x-axis you have, I don't know if you can see that too well, but I don't know if that's much of a difference, but you have the non-stuttering group, the control group on the left, in the normal condition at the far left, the rhythm condition next to it, and then the stuttering group in the normal condition and the stuttering group in the rhythm condition on the far right. And what you'll kind of notice is that, first of all, the stuttering group has a much greater variety of speaking rates than the control group. You'll also see that there's some effect where the rhythm condition, people speak slower in general than in the normal condition. So, and then I also added lines that connect individual subjects across the 2 different conditions. So if I wanted to control for speaking rate in the second level design, I was trying to figure out, oh, wow, I didn't even see that. Oh, I just texted. If I wanted to add some control into the second level analysis, I was trying to think of the best way to do this. So a couple of ideas that I've had thus far is to, if I'm looking at the rhythm minus normal contrast within a group, to also have the difference between the speaking rate and the rhythm condition and the normal condition. So it sort of gets this like, how much of the differences between rhythm and normal are affected by whether it's faster or slower in the rhythm condition than the normal condition. But then there's also, and so you can do that with either one. But then there's also this issue of, well, the stuttering group has more of a spread than the control group. So trying to account for the overall speaking rate within each group, so that we're comparing them at the same group and getting rid of the variability that potentially comes from this variability in speaking rate. And so I was thinking, in addition to, you could have two different covariates. One might be the difference between normal and the rhythm condition, and one might be like average speaking rate per subject. But that doesn't, I mean, I don't know if that'll quite capture the differences that are between those two conditions. So I don't know if you have ideas about a good way of doing that.
So it kind of depends on how are you thinking that conceptually this plays a role into the region activation differences. So if you just want to control for that because you think that some level of the activation difference are going to be explained by difference in actually speaking rate, and they are not meaningful to you because those might be actually difference within the speaking rate that also are apparent within the non-stuttering group, then that might be one thing. If you want to ask the question of just, well, no, I don't want to correct for those. I want to just think of them. I know that there is going to be some correlation between the mean speaking rate and the group difference because the stuttering group are just going to be speaking slower and they are not reducing their speech, their speed so fast, right? Their speaking rate in the rhythm condition compared to the normal condition, I imagine, right? I mean, you can actually run those tests initially, right? You could just look at those covariates and actually first evaluate, is the average between the two groups difference? I mean, in the two groups, and the average between the two conditions, right? And so I don't know, just by looking at the data, it's likely that there might be some difference in average mean rate between the two groups, like the slower in the stuttering group on average. And then in addition to the larger spread, there might also be a difference in the, but I don't know, because there is also, you have these three subjects that increase in speaking rate across the two, in the rhythm condition compared to the normal condition in this group. Yeah. So if you think this is not how do you check that is not an artifact? Is that something that is actually happening in the data, or is it something that is a problem that it might reflect a problem in your measurement device?
I have not checked that actually.
I mean, just to make sure that this is like true data before Glenn Carnegie is trying to extrapolate too much from that. But it's, so the first thing, kind of like try to understand what is going on from the data itself. So there's basically, is this first like a true thing in the data, or is this some sort of artifact? If it's actually some true effect in the data, is there any difference in the average difference in? You can actually do like a ANOVA on this data, like looking at whether the difference between the rhythm and and the normal conditions, the difference in the mean rate is different in the two groups or not. It seems to be larger, like negative in the non-stuttering group compared to the stuttering group, but that might be just an artifact of these three individual subjects, or it might not. It might actually be in the data. So it might be like first a good idea to try to understand those differences, whether some of those are significant or not on the actual mean rate, and then it depends on how are you thinking of how this mean rate plays in terms of the activation difference. Is it going to be the same across different regions, or is the way that mean rate affects activation, do you expect that to be different across different regions? Because on some of them it just might be like some nuisance type of thing, and in some regions it might actually be part of the role that this region has. It's a region has a role on the planning of the production. It might be just basically more involved in something when it's actually faster because it's a more difficult task, or perhaps some region, like all of the regions, also happens that for a faster production is also more difficult. So there are some like just an attentional issues that happen across multiple regions that is not more specific to something that is actually like indicative of the individual region role. So basically try to think about how mean rate basically relates to activation in the context of the question that you are asking. And once you have that figured out, then you can basically ask the specific questions to your data. Basically figure out first whether there are any differences or not in speaking rate across conditions or across subjects, and then whether those are true or artifactual. Then try to think kind of theoretically how those differences would play out in terms of activation, or at least how you would expect them to play out, whether they happen individually for all of the regions the same way and some type of nuisance effect that you want to control, or it's like something that in some particular regions that might have some particular role in the speech production, like mechanism that you would expect those differences to play out like a different role. And if you can specify that in a concrete manner, then that will should translate directly into a way of analyzing, or a best way of analyzing those differences. So basically, I wouldn't try to just basically enter all of the combinations into analysis of control covariates before trying to think about how do I expect those things to play out, basically, and what would I learn from asking this question and learning about. So if some region tells me that there is an interaction between mean rate and mean rate difference between the two conditions and the group in terms of their effects on activation, what does it mean to me? I mean, I think you need to figure that out kind of like theoretically first to better define which type of basically analysis you want to define here, right?
So, I mean, the main idea is that I want to make sure that when I'm looking at rhythm minus normal, the effect that I'm getting is due to the qualitative conditional differences where it's isochronous beat versus normal speech, but without taking into account the fact that they're at different rates.
Right, so like a control thing, right? So you're saying, well, I know that the rhythm, let's say that you have just a single group, let's say non-stuttering group, just to simplify. And so you're saying, well, I have this rhythm condition, which is, and people, just because it's a rhythm condition, speak slower. And I also know that I kind of know like how activation changes with the speed, because I have some type of variability even just within the normal condition and within the rhythm condition. I have some variability of how active I would normally expect activation to covariate with the speaking rate, and I want to control that. I want to say, well, what are the difference in activation between the rhythm and normal condition at the same level of mean speaking rate? For example, you want to compare kind of like the subjects in here to the subjects in here, basically. I want to say, is the activation of a subject that ideally I don't know, if a subject actually had remain constant in the speaking rate across the two conditions, would I expect to see still some difference in activation in this particular region or not? So if you're asking that question, then you definitely want to use that as a control covariate, and it would be the control covariate that you want to enter is the difference between the two conditions, because that's what you're trying to control. You're trying to reduce that to zero level. So right, you care about the zero level of the difference between the two conditions in the speaking rate. So you're asking the question, if the subject didn't change at all in mean speaking rate across the two conditions, what would be the effect of condition itself, right? So you're looking at a rhythm versus normal condition, and the average of that effect controlling for the difference in mean speaking rate across subjects. Does it make sense?
Yep.
Because conceptually it's kind of like the scenario that we had here in like age covariate. You're looking at the difference between groups at the same age level. So in this case, you are trying to look at the difference between conditions at the same mean rate level.
What would the conceptual difference be between implementing it this way and between having a parametric modulator at the first level?
Right, that's a good question. Let me see. If you have a parametric, well, it's a little bit different. This is just controlling of the variability across subjects, but it's never controlling about the variability within subjects. So when you have a parametric model, you are effectively trying to model for every individual subject how his or her activation is changing with the speaking rate, for example, right? And you are doing that within subject, and you get a measure that tells you how much the activation was for that subject for slow condition, and then how much his or her activation would change with his or her speaking rate. In this, and then you could just try to control for the level of the individual subjects and then enter those analyses into a second level analysis, or you could, but it would be totally different than what you're doing here. In this analysis, you are not trying to model what is happening within subjects. You are just saying, well, on average, I know that this guy has this activation on average across all of the normal speaking rate condition, and has this other activation on average, this individual subject, across all of the rhythm productions, right? And then what I'm trying to explain is the variability across subjects. So if I compare the subjects that are speaking a little faster versus the subjects, if I compare the subjects that are changing their speech a little more when comparing the rhythm versus the non-rhythm conditions versus the subjects that don't change that much their mean speech rate across the two conditions. Is there any difference in activation across subjects in this particular region between those different subgroups of subjects? Let's say big speed changers versus the non-so much speed changers, the ones that don't change as much in the mean rate across conditions. So it's a very different type of control and effectively also a very different type of question, right?
So, I mean, going to what we the recommendation is if we want to look at so if we wanted to look at a subject, what a subject looks like, what the rhythm minus normal contrast looks like for a subject that doesn't change,
Mm-hmm.
that would be slightly different than if you were to try to separately estimate some effective rate in one condition versus another condition, and then compare those two conditions at that level, right? Or is that not the same? Like,
right. So if I understand correctly your question, you're saying if I want to compare the subjects so basically I enter this kind of like difference in speech rate, mean rate across conditions as a control covariate in the difference between when looking at the average difference in activation between the two conditions across all subjects. Would that be different from actually trying to model each individual subject by entering a parametric modulator of a speaking rate for each individual production, right? And then trying to control it at the level of individual subjects. Is that the question? So basically trying to estimate for one individual subject what his or her activation would be at some particular level of speech of mean rate. Is that the question or not?
That's a question I have. Like, is that similar? That's basically your question.
Right. Well, I was thinking SRT did.
Because
We explored it at the first level and decided not to include it, but were we controlling it in the way that we wanted?
Right. Well, let me see. It's a slightly different type of control, right? Because in one of them, you're trying to model basically how a speaking rate changes within subject. Well, how activation changes as a rate of a speech rate within subjects, and try to estimate what the actual activation would be for that given subject. But well, let me see. If you do that. If you did that kind of jointly across all of the conditions, so you don't have any like interaction between a speaking rate and condition. So you assume that the change of activation as a function of the speech rate is constant. It's just a number basically, and it's constant across the two conditions, so it doesn't change in the rhythm versus the normal condition. And then control, and then get an estimate of where the activation would be at one particular speech rate level for each individual condition. So basically you try to kind of like normalize within subject the two conditions by correcting for the speech rate differences between the conditions separately within subject, how that would be different from controlling like for that level at the subjects level, at the cross subjects level. Well,
it might be actually, now that I'm thinking about this, it might be more meaningful to look at the differences, because if you're estimating them separately, you're not taking into account that there's some relation between the two different, for an individual subject and the two different conditions that are potentially linked. Unless we moved on to a different question.
Right. I mean, it might be effectively the same question. Basically, you might be actually trying to answer the same question in two ways. You will be effectively answering the same question, which is basically you are trying to control for potential difference in a speech rate across the two conditions, only that you are trying to control separately within subject, or you are trying to control basically across subjects. I think it's probably mostly a matter of practical. So I'm unsure whether at the level of individual subjects you are going to be able to control for that in a meaningful manner, while at the level of across subjects that is probably going to be a more obvious effect, or perhaps simpler to control for. So what I'm thinking is that if it kind of like depends. If you don't have enough repetitions of different speech productions with different speaking rates within subject to basically get a good estimate of how speech rate changes within subject, then that control is going to basically add noise and not correct that well for potential difference between speech rates between the two conditions, because the level, that effect cannot be measured very well within subjects. So in that case, you will probably be better off trying to control it at the second level. So basically, just instead of trying to control it for every individual subject, just try to control it across subjects, basically by looking at the difference between the subjects that change a lot in terms of their speech rate between the two conditions and the subjects that don't change that much. And the effect might be a little bit more visible in this, like between subject comparison compared to the individual subjects. But if you can get away with actually doing the control at the first level, at the individual subject level model, I think kind of like theoretically there is a stronger control, because that also basically allows you to estimate in a well-defined manner for every individual subject, allowing for potential interaction. So basically, not every subject is expected to change their activation level at the same rate with the speech rate, right? Some subjects might be like changing faster or the amount of change in activation for like a fast speech or a slow speech might be different for individual subjects. So if you are able to control it for individual subjects, you are gaining that additional level of control of that effect. But the question is whether you can actually get away with that in terms of practical significance or sensitivity or power. Basically, do you have enough repetitions to actually be able to control for that in a meaningful way within subjects? And if you can't, or you think that you might not get away with that because you don't have enough repetitions, then it might be like the second best option will probably be to do that control across subjects, which was what I was originally suggesting. But Lane is probably right that if you can get away with doing that control at the individual subject level, that might be even stronger, because that would also allow for potential interactions between the amount of changes in activation that correlate with the speech rate for individual subjects, which you're assuming just a constant thing across all subjects in the former, while if you do that separately for every individual subject, you allow for that effect to be different for every individual subject. But again, that I'm not totally sure whether that is possible or, well, not possible, where you can actually get away with that, doing that, basically. You have the power, enough data to actually get that control robustly, so to speak.
I think I'm a little bit lost, but I actually have to go anyway.
Sorry, I cannot hear you. Can you hear me?
Discussion, like start here the next day.
Let's see, 1 second.
Can you? Yeah, you got really soft recently. Very quickly.
I don't seem to be able to hear you guys.
It seems like, well, you certainly want to be very careful to not do both, right? To like try to remove the speech rate effect at the individual level and then enter speech rate in here.
Right,
but it could be something where, well, we can let you go.
Yeah.
I don't know how to hear us.
Oh,
Yeah.
You can't hear us again? Darn it. What happened? Oop. How about there?
Can you hear us now?
It seemed like there was a connection issue at the other end.
Yeah.
Well, let's call it.
Yeah.
To try to remember right where we are. Maybe we can play the last 5 minutes of this one recording before we start up the next meeting.
Yeah.
We should definitely, like, one of these meetings where we feel like we're actually going to move on to looking at